Yes, we'll start within 2 to 3 more minutes. Okay. Yes, is my screen visible? Hello?
Yes, sir.
Yes, the screen is visible, right? And see the slides are moving?
Yes, yes. Slides are moving, sir.
Okay. Maybe on my side there is some little latency, but you can see the slides are moving, right? Okay.
Sir, we can start directly problem.
Yes, yes, just 1 minute. My slides are not moving. 1 second. Yes, yes. So, any one of you, if want to get any doubts clarified, you can just ask, or else we can just move to the problems, right? Because there are still a few number of problems that are left. So, you want me to clear some doubts, or want me to proceed? If you have some doubts, feel free to ask. I have some slides on the doubts, so I can just explain there. So any doubts regarding any topic, because today is the final session and tomorrow is a recap session. There also we can have some doubts. Otherwise we can just jump into the problems, right? I hope I am audible also. So otherwise we will just move on to the problems on the converters, some remaining problems of PhDs and all those parameters are there which we can have into the numericals. So shall we start, or have you have some doubt? No one of you are telling anything.
Yes, we can start, sir.
Yes, so we
Sir,
can start. Yes.
Sir, in a previous question, you spoke about UAPC.
Yes.
We calculated the RMS current rating and VA rating of the shunt element.
Correct.
So, sir, if we have to calculate that for the series element,
Yes.
we will calculate that from the voltage side.
Yes, and you have the load information with you, so you can get the current from that. So VA rating means, I told you, two things you have to calculate. One, any for series or shunt or anything, you need to first consider that how much is the maximum voltage. Rating means what? It is worst case scenario. You have to consider what is the maximum voltage that can appear across the filter and the maximum current that it has to handle. So current information will come from where? Load, because load is connected, and your voltage information will come from the nature of the filter that you are using, from power balance and all those things, whether it is UFPC, what type of UFPC, what type of voltage it can inject from that, and what you want to achieve finally. Okay, so that will give you the information or clue or hint to calculate to write the equation, and then from that you can derive the voltage, maximum voltage that it has to inject. By voltage and current information, you can just multiply and get the volt ampere rating. Okay, so either it be series or be, I think some series problems are also given in the assignments also, you must have seen, so that those solutions are also there. So UFEC, you just good evening, sir.
Yes, sir. Hello.
I was telling, I'm audible, right? Hello?
Sir, sound was breaking. Now you are audible, sir.
Yes, so what I was telling, that for either it be series or shunt, okay, you have to calculate the voltage and current parameters, worst case scenario voltage and current, and as for that, you have to calculate the volt ampere rating. Okay.
Yes, sir. Yes, sir.
So the voice is not breaking, right? Green is, I don't know why.
Yeah.
So we'll start the problem on the converters, right? The first problem is here. So I hope the slides are visible. So see the first problem. So we have a 3-phase 12 pulse bidirectional boost AC/DC converter, and which draws 30 kilowatts from 254 volts per phase, 3-phase AC mains with sinusoidal wave voltage. And that is you are having this kind of arrangement. Slides are visible, right?
Yeah, visible.
because I cannot see.
The slide is not changing.
Yes, so sorry for the interruption. Okay. So I hope now the slides are visible. Okay. And voice is also clear, I think. One
Yes,
of you
sir.
can just confirm.
Yes, sir. Yes, sir.
Yes. So just the problem is a simple problem. They are only asking you because you know that on the AC side after the converter you have PWM voltage. Just we were discussing in the previous week, right? This kind of problems. So what they are asking you, since you are in a course of power quality, so you need to be fluent with the harmonic analysis. So what they are asking you is to determine the RMS value of the 11th order harmonics of the current, not the voltage. Okay. So just read the problem carefully first and tell me how you can do that. Because a lot about the harmonics and power transfer we discussed in the previous week. So just by reading the problem, what can you, because one more point, you just note that the displacement factor is corrected close to unity. When displacement factor is unity, what can you apprehend about the supply side? Or else tell me whose displacement factor is actually corrected to unity. Is it the supply or the load or the converter? Whose displacement factor are we talking about? Just intuitional reply one of you can say that here this line is telling that displacement, sorry, this displacement factor, yes, this displacement factor is, one second, this displacement factor is corrected close to unity. Whose displacement factor are we talking about? If anyone, if you can tell me.
Load side, sir.
No, I told you Ganesh, right? Yes.
Yes, sir.
So what I am telling, yes. So see, load power factor or displacement factor or anything is not in your hand, because customers will connect whatever kind of loads they want to your supply, and our electrical power system is designed in such a way that you should always be ready. From a generation perspective, you should always be ready to supply the power of any nature to the load. May it be at unity power factor, may it be at unity power factor of the load, or may the load be at 0.8 power factor. We cannot deny to supply them some power. But what we ensured is that our supply side is not operating at non-unity power factor. We can ensure power factor correction at our supply side, and then also we can supply the reactive power to the loads by plugging in some capacitor banks or some active shunt compensation techniques that we have learned. That's why the active load side consumers and middleware there needs to be ensured by some system operators that some compensation is enabled such that both the loads get their required power and active power, and both the supply is not also distorted, or the reactive demand from the supply also does not exceed the threshold as per the guidelines, right? Because I told you losses needs to be paid by the grid operator. If more losses are happening due to drawing more currents due to non-unity power factor at the supply side, then who will pay for the loss? That's why we want power factor regulation at the supply side. So displacement factor is corrected to unity, or whatever you learn about this kind of DC-DC problems like PFC, AC-DC stage conversion, all those are talking about the PFC, the power factor correction of the supply side. First and foremost, this needs to be understood, right? Now, you have the 3-phase 12 pulse bidirectional boost AC-DC converter. So that is nothing but that AC to DC conversion stage. You have deployed first. You have deployed bidirectional, means you have a converter sitting there, and not the diode bridge rectifier. You have the bidirectional switches, IGBT based. It is written IGBT based voltage source converter, and the load is given to you. And since in this kind of problem, I also told you that don't assume any kind of losses in this kind of problems, because we are not given information about the losses. So whatever is the AC side input power, I'm talking about watt, so that should be the equal to the load active power demand. So power generation and power demand, or power demand from the grid or AC supply, equal to the load power consumed. We can assume like that, power balance. Okay. So see, 30 kilowatts is being demanded, and it is supplied by the whatever is the AC source that is supplied. Okay. From 254 per phase. So 254 volt per phase and 50 hertz 3-phase AC means sinusoidal voltage. So on that side, we are talking about the power factor correction. So displacement factor close to unity means that your sinusoidal voltage and current, that is fundamental component of voltage and current, will not have any phase shift between them. That is the meaning of DPF equal to 1. Okay. So your voltage and current will be in line. Fundamental. Okay. V1 and I1, if I tell like this, so both will be like this. Okay. In line to each other. No phase shift. So that is the meaning of DPF equal to 1. Where cos of theta, where theta is angle, is equal to 1. Theta is 0 degree. So likewise, it is given. And the VSC is operated in a mode. So you are providing some load compensation, right? To cancel 5th and 7th harmonics in VSC output voltage. So you are compensating the 5th and 7th. So now you are being asked to calculate the RMS value of the 11th order harmonics phase current. Okay. So can actually calculate for these kind of problems. So now we are dealing about the current, okay, not the voltage. Previously we did a problem, I think also for current we did one problem. So 5th and 7th harmonic cancellation technique is incorporated in the voltage source converter, so that those voltages will not appear. But what you are asked in the question is to calculate for 11, because 11th will appear, because you are not compensating for the 11th. So 11th your harmonic ripples will come in the voltage. So for that, some 11th harmonic currents will also appear. Why? Because your displacement power factor can be unity. Can someone tell if displacement power factor is unity? Does it imply that power factor is also 1?
Yes.
Someone please.
Yes.
No, sir.
No, right. Because what is power factor? Power factor is displacement power factor into distortion factor. Displacement power factor means, this slide all of you take a picture, otherwise all of you will do big mistakes in the exam. And none of you will get any marks if you don't remember these simple concepts, okay? Because this is very important. Right from the beginning of the session, I am telling you what is power factor. Power factor is the phase shift between fundamental of voltage and current. So theta, if theta is the lag, so cos of theta is dPA. So one part is this. What is distortion factor? Can anyone of you recall and tell me the definition of distortion factor? Just recall and tell me, because this stage it is important.
Fundamental component upon RMS component.
Yes, can you repeat?
Fundamental component upon RMS component.
Yes. So if you see, so tell me the answer. You tell me. So why? If displacement power factor is 1, means there is no phase shift between the fundamental of the voltage and current signal. So because cos 0 is 1. Okay, I agree. Then necessarily power factor need not be 1, because if the load current is not linear or it has some harmonic distortion, then even though its fundamental component matches with that of the voltage, you see the waveform. It is not sinusoidal, but still dPF is 1. However, distortion factor is not equal to 1 because it has some non-linearities or some harmonics in it. So distortion factor cannot be 1 if it has some harmonics within it. So distortion factor is not 1 means that power factor not equal to 1 in this case. So load will decide how will be the power factor, that its harmonic components together along with its reactive burden will decide what its power factor will be. So two components will come. These components decide the active and reactive, and these components decide the harmonic content. So if this component is close to 1, then means that harmonic content is low. If this component is lower than 1, then it means that it is having more harmonic components and small amount of fundamental is present. Since small amount of fundamental is present and most of the signals or amplitudes are dominated by the higher order harmonics, means that distortion factor is much away from 1, much below 1. So in such cases, your power factor will not be unity. So displacement, if I frame a question like this, that displacement power factor is unity, can anybody comment about that power factor of the supply? What will be the answer? If I ask you a simple MCQ type question that displacement power factor is 1, then power factor is what? Is 0, power factor is 1, power factor is 0.8, or power factor cannot be commented. So
Be commented.
cannot be commented, right? If I give you some extra information, maybe you can comment whether it is lagging or leading. If I give you some more hints and some more, I can say, information about the system, then some of you can tell at least about the nature of the power factor, whether it is lagging or leading from this term. The hint is that which term of these two will give you the information about the nature of the active and reactive, all those things, this term. Because this term is taking care of fundamental components. And I told you that power transfer, whether it be active or reactive, will happen only because of the fundamental component of the voltage and current. Because here voltage does not have any distortion. I'm talking about the supply voltage, not the inverter voltage. So supply current, if it has some distortion, then for those harmonic currents, no power transfer will happen. Only for the fundamental of voltage supply and fundamental of supply current, when the power transfer will happen, active power transfer. I'm talking. So likewise, okay. So up to this, any one of you has some doubt? Or get it clear, because most of you are telling the wrong answers. Because marking up will not give you the answer, but if I frame it little difficult, little different question, then you can make mistakes. So if your concept is clear, then you will not make the mistakes, right? I can frame easy questions, but not as per the questions like this. But if your fundamental is correct, small question you can solve in one line. So likewise, you prepare. So coming to the question, what can you do? Any idea? Want to hear some answers? The question is clear, right? Anyone tell me what is this voltage? 254 volt per phase. Read the question carefully, okay? First, read the question carefully. So 254 volt per phase, what voltage is this? Please be careful, okay, and read the question and just be interactive.
This is, sir, supply means voltage is converter is consuming.
Correct. So if I write VS, but you can write
Sir, slide is
254
not
volt
changing.
per
You are
phase.
changing the slide, sir. Okay, sir.
I can see it is visible in the computer screen. It is moving.
Yes, sir, changing.
So what I am telling, that supply voltage is given to you, 254 volt per phase, right? That information is given to you for this system. Now what else information is given? The frequency is also given of the supply, which is 50 hertz, right? And power, I told you, input power, output power, that is load side and supply side, you assume to be same. So what is that? 50 kilowatts, right, is given. Or sorry, 30 kilowatts. What is it? 39. You can take a photo of this problem of the previous slide and we can then move to the next slide, right? Otherwise, I can also take. This problem, you just take some screenshots or something like this, and in next slide we will move.
Okay, sir.
Otherwise, you cannot see the data, right? Because you have to read the problem all the time. And first time you read carefully, then next time onwards you can solve. Taken?
Yes, sir.
So you know that after the converter there is an interfacing inductor, right? That value is also given to you. So AC inductor value is given as 5 millihenry. So what is happening if I draw the waveform? If I draw the circuit diagram, then you have the three-phase AC supply. After you have the converter, and then you have the AC load, right? About load, nothing is specified, so it may be DC or AC. But since it is DC, AC to DC, so load I can assume as DC load only. And here I am talking about this interfacing inductor, right? Because whenever you interface some converters to the AC mains, the converter will be having. Can any one of you tell why these inductors are important? These are LS, right? Why these inductors are used? Whenever you connect some inverters which is switching with some harmonics switching frequency, and the harmonics are there in the as in the form of switching ripples, switching frequency, because whenever an inverter switches, there is some harmonics, right? Because your inverter is switching, so some levels are coming in the voltages, and you want to make that voltage sinusoidal. So obviously some harmonic content is inherently there. So why you need this inductor?
Sir, because of filter.
One answer is that the higher order voltage is suppressed, voltage harmonics are suppressed as a filtering action. And another reason, can anyone tell me why these inductors are important? I told you in the previous week that in inverter, if you see from the DC side to the AC side, it acts as a. Can anyone of you remember? Right, it acts as a buck converter. So seen from the AC to the DC side, it acts as a boost converter, right? So the this has many interpretations, like synchronous machine you must have seen. Two nodes, this side voltage is different, this side voltage is different. So power transfer can happen. An inverter is also can be modeled as a synchronous. So power transfer can happen. One reason is that LS having for the phase shift between the voltage angles such that the active power transfer can happen. Other way to see this as is like that is a boosting action in the power frequency, not in the DC, but in the power frequency, 50 hertz, okay, 20 millisecond in one cycle. So that action is from the AC to the DC side. So the inductor is there. So power transfer and also minimizing the harmonics, that inductor is useful. Now also how the switching is done, that will also decide what harmonic components you want to compensate for. And accordingly, you can achieve power factor correction by multifunctional control. You can, of this inverter, you can achieve power factor correction or load because this load is DC, I am not talking about reactive power, but and also displacement power factor is 1 given in the question. So no, I am not talking about power factor, but harmonically it may be distorted, right? There may be harmonic distortion. So that harmonic distortion can be minimized by proper control also, where it is told in the question that third and fifth are already not there, right? Sorry, fifth and seventh, because third will not appear. Can any one of you tell in a 3-phase 3-wire system, can third harmonics exist? Can third harmonics flow in a 3-phase 3-wire system? Same, this is one question, and also for you another question, 3-phase 4-wire system. Can third harmonics flow? See, I can directly solve, right? But that will not give you any meaning to the question, and you will not understand the problem actually. That's why it is important, right? So answer these two simple questions. Can a third harmonic signal exist in the form of current? Simple. Assume. So in the supply, if can the 3 third order harmonic currents flow in the AC supply side? I want to hear the answer from any one of you. Just be interactive, okay? Yes, please. Please feel free to answer, right? That will clear your concepts.
3-phase 3-wire system, third harmonics will not flow, sir, since neutral is absent.
And why is so? Why the presence of neutral can guarantee the flow of third harmonics? Be a little more clear about that. Why the presence of neutral allows the flow of third harmonics, and why the absence of neutral, that means the 3 is only without neutral does not ensure or does not enable the flow of third harmonics. What is the main reason why it is so? Anyone? Well, after you understand the circuit diagram and after you have the concept clear in mind, problem is one line only. But the circuit diagram, you should be able to draw some form of diagrams, understand what the problem is talking about, and then it is one line, 1 minute problem, right? So tell me why the third harmonics cannot flow in a 3-phase 3-wire system. Agreed that neutral is not present. That's why it is a 3-phase 3-wire system. Now, why the absence of neutral blocks the third harmonics? Can any one of you tell me intuitively? Yes. Hello. Hello.
Yes, sir.
Yes, please tell.
Sir, through neutral, we can means unbalanced current or harmonic currents, maybe.
Sound is coming. Sound is coming from your end. Noise is coming actually. So hi, now you can speak. No noise is there. So now, this is important question. So why the absence of neutral blocks third harmonics is the reason, because if you see actually a AC circuit, right, and you have some currents.
Because the third harmonics will be in a sinusoid.
Correct. Third harmonics is sinusoidal, but how it looks?
It's similar to the fundamental frequency.
And about phase shift, what can you comment?
120
degrees. VA3 is V3 sine 3 omega t. VB3 is V3 sine 3 omega t minus 120 whole of 3 times, right? That means the third harmonics. VC3 is V3
yes,
sine 3 times omega t plus 120 degree. So what is 3 times 120 degree? It is 360 degree. So they are co-phasors, right? And if you draw in the sinusoidal domain, oscillation in time domain means rotation in phasor domain. And rotation is like co-phasor, all will rotate with the same without any phase shift, right? Because phase shift is 360 degree. So these kind of currents, if flow in these three phases, in a three-phase, three-wire system, does it satisfy Kirchhoff's current law? KCL satisfied or not? For third harmonic?
No, no, sir.
So it cannot be, right? If you flow 5, and if you flow 5, then it will not be possible. The current cannot flow because the electrical network naturally restrains such harmonics. So that is the reason. So third harmonics cannot flow in a three-phase, three-wire system. So no, the third harmonics cannot exist, right? But for three-phase, four-wire system, KCL not violated because the remaining unbalanced current will flow through the neutral. So yes, third harmonics can exist. That was the thing. Okay. So now coming to the question, it is simple one line. So can you tell me what will be the power transfer from here? Can you tell me current amplitude? What is I? P is root 3 VLIL cos phi, right? Cos phi is 1. So P is root 3 VL1 IL1 cos phi 1. Because phi 1 means the fundamental displacement factor. Because for third harmonics of voltage and third harmonics of current, there may be some different displacement factor. But we are talking about the fundamental, right? Because power factor exists for fundamental, displacement power factor and distortion factor. So displacement power factor only sees the fundamental voltage and fundamental current, phase shift between them. So theta 1. So now what is IL1 or IS1 you write, because we are doing for the supply side, so source side. So IS1, what is value of IS1? P by root 3 VS line to line, okay, fundamental. This is line to line voltage, don't confuse. If you want to apply phase to phase, then 3 times of V phase, I phase into cos phi. That should be there. So P is root 3 times VL1, IL1, V line to line 1, I line to line 1, cos phi 1. Or else someone can write P as 3 times V phase 1, I phase 1, cos phi 1. Both are same, right? So I do with line to line parameters. So what is IS1? Line current. Root 3 P by root 3 V line to line into cos phi 1. So what is the answer coming? Can any one of you tell me the value of IS1? Just calculate and tell me. Phi 1 you know 1. Sorry, cos phi 1 you know. Cos theta 1 is 1 because displacement power factor is given. This is displacement power factor, right? So this one, you just plug in the values because in the problem 254 volts is given as phase voltage. So what will you do to convert it to line voltage? You can do by phase formula, right? P by 3 V phase into cos phi. But assume a line. What is line? And since nothing is given about the supply, to consider that it is a site. I told you in the very beginning. And so if 254 volt is the phase voltage, what is the line voltage? Root 3 times, right? This phase RMS voltage. So line RMS is P by root 3 times 254, right? And this 254 is phase. So line means root 3. Multiplied by cos phi 1 is 1. So this step is clear. P by root 3 phase to phase. So plugging it in here. Root 3 times V phase to phase, right? V phase to phase is 254. So what is V line to line? RMS root 3 times V phase to phase RMS. V phase to phase RMS is 254. So V line to line RMS is root 3 times 254. So you plug it in here. Line to line. Then what is line current? Can anyone calculate and tell me? IS1 RMS.
$39.37.
Just let me once calculate. $39.37, correct. So this is what? Fundamental supply side current, RMS current of the star network, because nothing is given, so you assume star, right? So fundamental RMS current, okay, of the star network supply.
And I was like,
Okay, so
oh my god, I love that
sound is
word.
coming.
What does it mean? It means fine. And I was like, from then on,
Vijay,
the girls used to all the time. You know, I just the bottom of this
can you please mute? Sound is coming. Vijay power. Mute from here.
And I was like, oh my god, I love that word. What does it mean? Oh my god,
Vijay power, sound is coming.
and I was like, from then on, me and the girls used to all the time. Like, you know, I just love the bottom of this cup. I just love the bottom of this bar. I just love the word.
Mute.
मेरे पापा ने मुझे पढ़ाई कर दी
Thank you. So what I was telling, the supply side now, the screen is visible, right? So what I am telling, the supply side fundamental current RMS component now, or you calculate the sorry, one second. Yes, so what I was telling, you have the supply side current fundamental component, right? So why we need the supply side current fundamental component? Any one of you? What we are actually trying to calculate? I told you that the interfacing inductor is interface between the inverter and the AC supply. AC supply will not have any kind of distortion. It is purely sinusoidal. But your inverter is compensating only for the fifth and seventh. Otherwise, it has some switching harmonics and other harmonics, higher order harmonics in the voltages. So for that, some currents, harmonic currents will also come because of the nature of the two voltage and the impedance network between it, the inductor sitting between it. If I know the fundamental IS1, that is the fundamental RMS side component, then can any one of you tell me what can I determine? Because what am I asked? I am being asked to calculate the 11th order harmonics phase current. That is the RMS current, right? So see now, in the next slide I will do. So I can just yes. So this part you understood, right? Third harmonics part. So I am just erasing. Please make the circuit diagram and all system diagram clear in your mind. Otherwise, it is very difficult to understand without diagrams. So we have up to this 39.37, right? So this part also we can erase. Yeah, so tell me the answer. Why you need your anyone of you is free to be interactive, right? Please think analytically, we will reach to the solution. Why? What we need the 11th harmonic current component. Who will give me the 11th harmonic component RMS? From where can I calculate? Yes, hello. From which parameter can I determine the amplitude or strength of the harmonic currents in the phase? From the harmonic voltages, right?
Yes, sir. 11th harmonic voltage.
Well, yes. Please be interactive. The harmonic voltages will only give me the information about the harmonic currents. So to determine the harmonic voltages, because you know how the PWM voltages look like, it is a square wave. So for square wave, we already studied that if we know the information about the fundamental of the square wave, we inherently also know the information about the other harmonic components of the square wave. So if somehow we can determine the amplitude of the fundamental or have some information about one of the harmonic components of the square wave that is sitting here, this node, at the inverter nodes, right, where the actual harmonic voltages will appear, the PWM voltages will appear, like pulsed square waves. So if you have any kind of harmonic information or any information about the amplitude of any one of the harmonics of that pulsed PWM voltages of the inverter, then you inherently know the information about the any of the harmonic components. And from there, since you know the information about any of the harmonic components or their strength and all those things in the voltages, from that you can calculate actually the your value of the RMS component of the currents in the harmonics, the harmonic currents in the supply. Agreed or not? So this grid actually, this is forming the grid, right? So don't assume that one grid is sitting here. It is symbolically symbolizing the grid, but these are the supply nodes, right? Here you get the voltages. Maybe it is a battery and it is just taking some charging current and just the voltages, AC voltages are appearing at the terminals and you connect it to the grid like that you assume. So this is the juncture point and we are talking before the inductor at the this side. So the PWM voltages are appearing. Okay. So that is what we are talking about. So PWM voltages are for 2 level. How does the PWM voltage look like? Anyone? Square, right? So for
Square,
anyone
sir.
can tell me, yes. So if I know the amplitude of the maybe peak or RMS of the fundamental, can anyone tell me what is the voltage amplitude of the nth harmonic for a square wave?
By n, sir. By 11.
VS1 is, for example, VS1. Amplitude I am telling. Maybe peak, maybe RMS. I don't bother, okay? So VSN is what? VS1 by N, okay? 1 by N times for a square wave, remember. So if I know VS1, I know VSN as VS1 by N and ISN as, what will be ISN? The voltage across the inductor is the harmonic voltage, right? So this harmonic voltage you determine divided by the impedance offered by the inductor to that harmonic voltage. What is that? N times? N times omega L, right? So what is that? N square times XL or XL1 you can write. So now the main big question is, because N you know, because 11th, for 11th you need to determine. XL you know because you know the value of omega and L. But who will give you the value of VS1? Tell me. Because this side is purely sinusoidal voltage of the grid. This side harmonic voltage blocked by the inductor. That's why we took the voltage across the inductor at the harmonic voltage and then we divided by the impedance offered by the inductor to those harmonic signals and then we determine the current. But how can I determine this side voltages. By simple phasor diagram, right? So what is that? If I know that this side is purely sinusoidal Vs and Is I know to be unity power factor. So Vs minus Is excess, J Is excess, okay? Because this is inductor, right? So how will the phasor diagram look like? Multiplying by J means plus 90 degree anti-clockwise. So J Is excess, since Is is like this, Is into J. So like this is plus minus like this. Because this is the anti-clockwise direction, you take it to be positive. And Vs minus JIS excess, because drop, inductive drop is there for the fundamental also. For the fundamental also, there exists some voltage drop. So that voltage drop, after that you get the fundamental of the PWM. So if this is Vs1, which is inherently purely sinusoidal for the grid, minus JIS excess fundamental will give you VPWM1, whatever name you want to call it. So can any one of you calculate? You just use Pythagoras theorem, right? So Vs is 254 phase. I'm talking about phase. Per phase you do because this is a three-phase network, right? Per phase impedance is there, right? So per phase, and then you take a KR by into √3. So 254 is the phase plus Is excess. What is Is excess? Whole square whole root over is VPWM1. So this is not S, this is PWM, okay? Hope you understand why it is PWM. Because supply at the grid will not have any harmonic distortion. The inverter PWM voltages are having harmonics. That's why we denote by VPWM. So VPWM1 by N is the VPWM That is the strength of the nth order harmonics. So to calculate that, we are using the reference of the fundamental and the information of the nature of the waveform, which is squared. For that, we are only able to calculate. So now you tell me, what is the VPWM1? 254 square plus Is into Xs. Is means Is1. So Is1 we know because we are funding for the fundamental. So everything fundamental we take. And Xs also you take for the fundamental. Xs1. So what is that? Calculate and tell me. This will be easy. Is1 you know 39.37 and Xs is what? Omega into Ls. Omega is 2 pi into 50. Because 50 is the fundamental. And Ls you know, Ls value 5 millihenry. Plug in all the values and tell me what is VPWM1. After you determine VPWM1, put in n equal to 11 and XL you already know. So calculate the value. Tell me the two different values, VPWM and you calculate ISN. The 11, IS11 you calculate. Okay. This should be now easy. Please calculate. Because this exercise was important for you for the first problem, right? Second problem onwards, it should be easy for you. Please be fast because we have the microgrids to be covered today only. We can devote another 15 minutes and then we can move on to the microgrid problems. Microgrid, if you understand the problems, will be easy. So no need to worry. We can cover that in 40 minutes and we can devote 10 minutes for this.
PWM is 261.4.
VPWM is 261.4. Let me check. Yes, correct. And from that VPWM fundamental, you use the reference of the square wave and calculated VPWM 11, which is 1 by 11 times VPWM fundamental, which is 1 by 11 times 264. And again divided by n times XLS. That will give you the value of the strength of your harmonic current, right? So tell me, what is IS11? Because there is no shunt path for IS11 to flow. That's why we use the regal filters, right? If you provided shunt filters, that IS11 would have flown to the shunt filter and the supply side current would have been purely sinusoidal. But here supply side current is not able to be sinusoidal since you have some amount of harmonic voltages in the inverter. And those voltages in the form of currents are not being able to find the path to the shunt. So they are appearing somewhat in the supply. That is the full essence of the problem. So that's why I think you to calculate the strength of the IS11 because this IS11 will appear in the supply. PWM voltage of the inverter will reflect as current also due to the impedance between the source, that is the grid, and the inverter. So that's why although the supply side is having displacement power factor as unity, we guarantee that it is not having power factor as unity. This part I think should be very clear. Why power factor is not being able to be unity? Because you are not providing a shunt path for the harmonic currents to flow, for which they are reflecting in the supply side. This PWM voltage are reflecting as harmonic currents in the supply side. Since they are not, there is no path for these harmonic currents to flow. Where they will flow? They will flow at the supply side, which will bring down the overall power factor from unity. It will pull down the power factor, not let it be unity. But the displacement power factor is still 1. It can be so. So remember this line that displacement power factor equal to unity does not ensure your power factor is unity. That was the full essence of this problem. Now we calculate IS11. What is IS11?
1.376.
Correct. So how you calculated? You just 261.4 divided by 11 square multiplied by 2 pi into 50 multiplied by 5 millihenry. I hope I am not writing it. It is very clear, I think, right? So let's move on to the next problem. Next problem is a follow-up question where they are asking you to calculate one. Yes, where they are asking you to calculate the THD. Simple. We have the information about the harmonics up to what? 25th. So once you have all the information about the strength of the harmonics in a AC signal, you can easily determine its total harmonic distortion. So what is the formula of total harmonic distortion? It's nothing but fundamental, that is how much is the harmonic content within the fundamental. The main essence is like this, right? So fundamental, so all the RMS of all the harmonic components divided by fundamental RMS. All the I11, I, yes, okay. So you can do for 17 and then you can do for what? 19 and then you can do for 21, then 23 and then 25. Now can anyone tell me, can I15 exist? Can I21 exist?
Oh, sir, third harmonic.
No, it is not third harmonics, it is a integral multiple. Yes. I hope you understand, because 15 into, if you do that 15 into 120, na, then divided by 360, then it is 5 times of 360, means it is 360 only. Likewise, it will appear as in the phasor diagram as a rotating with 15 omega and same co-phasor like the third harmonic. So I15 in a 3-phase 3-wire arrangement cannot exist. So similarly, 7 times of third, that also cannot exist. I21. I hope the screen is visible, right? Because in my screen it is lagging. Can you see I21, I23, all those things?
It's lagging, but it's visible.
So now it is coming. So what I am telling, the third components and its multiples, integral multiples, will lack in the 3-phase 3-wire arrangement. That is for sure. So now you calculate for these, because you know the formula, right? From here, VPWM1 you know. From VPWM1, IS or ISN can be calculated. What is the formula? ISN, that is strength of nth, is VPWM1 divided by n square into XLS, where n is the harmonic order. So calculate. So it is nothing but I11 square plus RMS, right? Square of sum and then root RMS. So you do up to I25, take the allowed signals and divide it by IS1 square whole root over means IS1 only. Because fundamental RMS, so tell me the answer. It is one line. VPWM1 you take common and then you do 1 by n square XLS, or VPW, this also can be taken common. So like a harmonic mean, right? HM 1 by 11 square plus 1 by 13 square, like this you proceed up to 1 by 25 square, and then VPWM by n, VPWM by XLS is common, and that goes away. Okay, and comes out, and this is within the root divided by IS1 is 39 amperes, right? So you calculate this, what is coming? Square will come. Okay, correct. So what will it be? THD. It multiply into 100%, right? So what is the answer? Tell me. This step is clear how it can. Anyone having any doubt, please ask me. It follows from here and here, from the definition of THD. You take common, you will get this. I will do with you. So what is it coming? PWM1 is what? 261.4, right?
That 39 stands for
The current IS1.
Thank
RMS. Or whatever you got. What you got? 39 point something, na? 39.37. This is IS1, right? IS1 RMS. So now 39 into 2 pi 50 into 5 millihenry, right? And this you multiply with whole root over of 1 by 121 plus 1 by 169. So how much is the TH? So XLS value is coming as 1.51 ohms. So this also you can plug in, okay? And VPWM1 is how much? 261.4, right? So now you calculate. Yes, any one of you. Did you get something? Please calculate and let me know.
So 63%.
63%. Kindly recheck. Oh, note this is a root over is there, right? Don't forget the square root. Square root is here. So if you calculate divide 169 plus 1 divide 625 and then you root it and then you multiply with 261.4, okay, and divide it by 39 and 1.5. So what is the answer coming? Tell me one by one the value of the strength of the currents. I want to show you something. I11, I13, I15, I17, I19, I21, I25. Tell me one by one the values. 261.4, what is it coming? Divided by 11 into 11 into 1.51. 1.43, right? I11 is 1.43, then I13 is 13 into 13, right? So 1.02. Calculating RMS, right? RMS amplitude. Then I 17 into 17 into 0.6, 0.59 you write. Then I19 0.4 amps. One is 0.39 amps. And then I25 is 0.27 amps. So now tell the RMS value of all the harmonic currents. 1.43 square plus 1.0 square plus 9 square plus 0.4 square plus 0.7 square. whole root over. So it is 1.9 amps, right? Around 1.93 amps is the harmonic current. So divide it by 39, you will get the answer, right? 4% I am getting. .9%. So this is divided by, okay. I did mistake in writing, and you also did not tell me. This term 1 by n square should be
To the power 4 inside under root.
yes. Whole inside under root we are taking out, right? So this is square will be square term will not be there, right? This I wrote right only. So what I was telling, see, I PhD means what? V PWM 1 by n square into XLS. You sum it, square and sum it, and then you divide by IS 1. And then you root it also. So this is the RMS of harmonics. So what I was telling you to do is, since your VPWM and XLS are same, you take it common, and since you have square over them and root, so this should be appearing outside the bracket, right? Into 1 by n square. Okay, so whole to the power 4 is also there, right? You understood? Understood or not? So this n square is the strength of ISN, but I need to square again and then sum and then root. RMS, right? So this should be, this is 1.5, this is 261.4, and IS1 is 39.37, and everything we wrote correct, but this sigma would be over n to the power 4, where n is 11 to 25. And obviously there should not be any 15 and 17. So if you do it, you will get around 4%. Want to do and check? .9. So 5%. Right, so I'm moving to the next problem, right? So PWM voltage, they are also asking the THD, right? In the voltage, in the current. So I told you already that VPWM is nothing but N is nothing but VPWM 1 divided by N. Slides are moving.
Yes, sir.
Writing is visible, my writing.
Yes, sir, but it is lagging.
So I will just do one thing. I will stop and reshare. So VPWM N is VPWM 1 by N. Doing this, the percentage THD in the PWM voltage is being asked. So it is easy, right? Because VPWM N summation N equal not equal to 1, and all the other harmonics you just square, sum, and then root, and then VPWM 1. That is the definition of THD, right? Do it and let me know. Same for all those harmonics component 11 and what you tell 13, 17, 19, 21, 23, 25. Sorry, 21 is not there. 23 and 25. For these are harmonic components, you let me know the percentage THD. PWM1 is given as 261.4 volts. Take this and let me know. DC voltage, PWM voltage, right? Should be easy, right? 1 by n and you square and then sum and then root. And then divide by the fundamental and multiply by 100. Give me the answer. What is percentage THD in the voltage? These are one line problems only. Just the voltage harmonics you need to consider. Square, add, root. Simple answer. The crest factor in this case. Simple. You must know the definition of these terms in power quality, these parameters or these ratios. So tell me, what is VPWM1? Sorry, percentage THD. What is the answer?
14.9%.
14.9, around 13.3 I am getting. Okay, it is acceptable. Around 14%, right? We'll keep the range, no issue. You just accurately calculate, okay? Don't assume too many approximations. Just as many decimal places you want, you just calculate. 2-3% plus minus we'll keep, okay? So no issue. Okay, so, but we try to be accurate, right? And not be, the range not be more, so there you should be more careful. So numericals on microgrids, right? I will do 2 numericals on microgrids, which will cover the whole thing. So before somewhat we were discussing about the solar microgrids. Can anyone tell me something about the wind microgrids? Just 5 minutes discussion we can have on the 5-10 minutes discussion, and then we can jump onto the problems. Before that, the slides should be moving. The slides are not moving. Just let me connect and reconnect. Now it is visible, right? Hello.
Visual, sir. Numerical on microgrids.
Yes. So what I am telling, the solar microgrids I already discussed with you that solar microgrids, we do MPPT, right, for the solar photovoltaic arrays. And what is MPPT? We told you in the last session. What is the meaning of MPPT? It is the electrical to vary the load line and intersect with the maximum power point characteristics for that given radiation. How we do that? Using a converter by impressing varying voltages, which is called as MPP voltage for that given radiation. The maximum power point voltage. This is the characteristics for different irradiations, and this is the maximum power point. So we try to follow this load line for R1, R2, R3, different radiations. We want to follow the load line in a manner dictated by the MPPT algorithm. MPPT algorithm somewhat P and O and incremental conductance, all those MPPT algorithms are there. We try to track that point and intersect it with the electrical characteristics. So there we use converters and try to impress the necessary voltage or the MPPT voltage across the PV array such that it can throw maximum power and push it to the grid. And we obviously utilize the voltage source converter here, which will convert the DC power to AC power. Now, can anyone tell me, is it a mechanical MPPT or an electrical MPPT for solar projects? Where we have actually the solar photovoltaic arrays, which you must have seen in the roads or in the buildings or in the rooftop. Is it an electrical or a mechanical phenomenon? Can it please be interactive? These are the basic concepts. So we just cover them in a 5-10 minutes, and I want some discussion. Some concepts which are very common, but you may not know. So that will help. So for these 5 minutes, please be interactive. Okay. So is it electrical phenomenon or mechanical?
It is, sir, maximum power point tracking means it should be mechanically means. Yes.
I am telling for solar. For solar microgrids, to achieve MPPT, are you doing any kind of mechanical arrangement or electrical arrangement? Mechanical means some tools you are using like gears and all those things. Here is it necessary, or here is it you are doing electrically by impressing particular voltage using control?
Electrically, sir.
Yes. So solar microgrids to be operated in MPPT, we are doing it electrically. And can solar photovoltaic array absorb power, or they can only deliver power? Is it unidirectional or bidirectional?
Bidirectional, sir.
How can solar store power? The solar arrays, when sunlight fall on them, they can throw power. That is supply power. Can they store some power? The solar arrays, whatever you see, the solar modules, also the government also announced, right, for rooftops, some solar schemes. So
They
there,
can
can you
give
store
power,
power
sir.
to the grid? You can only give power to the grid. Right.
They give power to the grid. Also, they can store in the batteries, sir.
In the battery, what I am telling, for the solar photovoltaic arrays can only
Give.
supply.
Yes.
If they specifically in the problem, if we are writing solar microgrid, does not necessarily mean there is a battery. If there is a battery, we'll mention it separately. Otherwise, how will you know numerical? If there is a battery, always there will be specifications of the battery or some lines that there is some battery actual. Otherwise, when we tell solar microgrid, it implies a AC microgrid. If they are tied to the grid, they are tied to the grid, that will be given to you, that statement. And they are tied with solar photovoltaic array, interface at the DC side. And in middle, there is a converter, the inverter, solar inverter. So that is the configuration. And such configurations can exist in various topologies. We already discussed, like single stage, single power processing stage, 2 power processing stages. Last session, you can see we discussed. So these microgrids are built to push the power to the grid. They cannot take the power and store it. unless until there is a battery energy storage. That you need to understand. Do some of you remember the term self-supportive microgrid, self-supportive DC link? Any one of you present in this session, do you recall a term self-supported DC link? Yes, I want to hear some answers.
Self-supported means that it is converting from the self, means
No,
taking
you must
DC.
not have seen the previous weeks. Self-supported DC link means there is no battery tied directly to the DC link. Or else, in other words, it means the DC link is maintained by the AC side and not DC side. Means to maintain the DC link, the amount of power, that is small amount of power that is required to charge, keep the capacitor, DC link capacitor charged in AC side. We tell a self-supported. Why self-supported? Because the DC side sources are not responsible in this case, in the self-supported case, to maintain the DC link. That's why we turned as self. Otherwise, if the DC side sources are deployed to maintain the DC link, like this, and there is a capacitor, and there is a converter, IGBT based, and there is a grid. Some interfacing inductors are there. So if the DC sources like battery is there, battery, some solar photovoltaic arrays are there, in between some converters may be there, some boost converters. So if the battery is directly there, who is maintaining the DC link constant, then you tell it as it is not self-supported, because someone is there sitting at the DC side to maintain the DC link voltage. But if someone is not there at the DC side who can maintain the DC link voltage constant, because the DC link voltage needs to be maintained, not constant, it can also vary, but it needs to be maintained by someone, because the capacitor needs to be kept charged. Otherwise, it will just stop the operation and the capacitor will discharge. This voltage needs to be maintained by someone, the DC voltage of the inverter. So if that is done from the AC side, you simply call it to be self-supported. If it is done by someone sitting there in the DC side like a battery, then it is still not self-supported. But can any one of you tell me, can a solar maintain the DC link? Can a solar photovoltaic array maintain the DC link voltage of the inverter? That's what I am asking. Because it is also a DC source. It can maintain to some extent. So can solar maintain DC link? If yes, is it in all cases? And what does the term DC link voltage maintain mean? Actual implication. So 3 questions I posed to you. Significance. 3 questions you can answer, you understood that thing. Then we can move ahead to the wind. So tell quickly. Can solar maintain DC link? What does the term maintain DC link means? Maintaining DC link voltage. What does the significance in terms of circuit theory? But if the voltage across a capacitor is constant or maintained, what can you tell about the nature of the operation? Whatever is the charge coming into the capacitor, to charge it is equal to the charge flowing out of. In that case only the capacitor voltage will be constant or maintained. Agreed or not? Hello?
Yes, sir.
So what I'm telling, to maintain, can you use the solar?
Yes, sir. We can use the solars.
We can use only the
means, sir, in self-supported DC link, sir, we are using the AC side
what
without
does
battery
what
and
does
with the
mean?
help of converter.
Now all thing okay. What is the actual significance of DC link voltage being maintained? What it signifies?
Means, sir, capacitor voltage are not changing. It is charged constant.
Constant, right? What
And
does it actually mean?
we are giving the charge from the solar array with the help of converter.
Correct. And what does that actually mean? Think deeper. Some power is who is taking either the load or the grid? Correct. Some loads may be also there. So what? The power flowing from the P into the grid.
Sound is breaking.
Scenario, the power balance is and satisfied. Some that is coming from your side. Ganesh.
Yes, sir.
You can mute also when it is not. You can mute. So what I'm telling, when the PV side is throwing power and it is fully utilized in the AC side, no power staggering is happening in between, then the capacitor voltage will not rise, neither will it fall. DC link voltage being maintained naturally signifies power balance. Whatever is the power coming, nothing is being stored. Significance of being maintained. Whatever power is coming is going somewhere. It is not staggered into the capacitor. If the power is staggered, then the voltage will rise or the voltage will fall if you have some deficiency. So the DC link voltage, because you can push the power and some part of it can be utilized in the capacitor and keep it charged. Because once you charge the capacitor and your power balance is met, that is the power coming in is going out, then the capacitor will remain charged to what value it was previously charged to. You can use the control and maintain its charge, and no additional power will be taken. Only some losses will be there, some small losses. Otherwise, no active power will be consumed additionally to maintain DC link voltage in further stages of the operation. Once it is maintained, it remains maintained. Only some small losses you have to stop. Three battery sources can DC link voltages using some proper control, either or the bidirectional converter of the battery or the converter itself from the grid. You have self-supported arrangements as well as you have DC sources which can maintain the DC link. So that is one condition, and once the DC link is maintained, then you can push the power of the solar, power generated by the solar, or can store some part of it into the battery. So all the thing you need to think in terms of power. PV pushes some power is stored in the battery, remaining power goes to the grid or feeding the load or selling the power to the grid. Likewise, you need to think for these kind of problems. Another thing you come to, wind microgrids are having wind generators. Likewise, you must have heard in the power system like synchronous generators as alternators, which generate power by having some DC exciters, which you rotate with a prime mover using some burning some coal and then pushing the turbines and using the governor settings. You rotate the prime mover by steam, and then the machine rotates and generates power, electrical power. Similarly, the wind turbines are deployed, which can rotate with the wind speed and can rotate the shaft of the generators. Whatever machine you can use, we can use doubly fed induction generators. Do any one of you have any idea of what kind of generators are used in wind turbines, wind conversion systems? One is the turbine, mechanical turbine, which have blades, which you see, and the nacelle, there is the arrangement, right? The generator and all those gearboxes are sitting there. So can anyone of you tell me some names of the machines that are used in wind energy conversion systems as generators?
Doubly fed induction generators, sir.
And other machines? Other name of machines? In the nacelle, they are all sitting, right? Nacelle means the three blades, behind that you have some housing for these generators. These generators are responsible for converting the mechanical power delivered by the turbine into the shaft to the electrical power. So this is similar to the power systems, like in the thermal power stations. We have the wind. It is renewable arrangement to rotate. This may be also a geothermal arrangement and hydro arrangement, all the likewise. But you tell me that these generators are some names like machines. You can tell that doubly fed induction generators or permanent magnet synchronous generators or BLDC or synchronous reluctance machines. All kind of machines you can use as variable speed machines you can use to push the wind power. Again, one question I want to ask you: wind generators absorb power or only deliver power?
We can, sir, also use normal synchronous generator.
Yes, all are possible. But you have to apply proper control to make them rotate at that speed which delivers the maximum power. And you need to have concept very clear in your mind that speed of turbine and speed of generator does not have any relation. Your wind will try to rotate whom? Please make this concept very clear, very interesting. In your future studies, you
it will try to move the gearbox, sir.
No, wind will try to rotate the blades of the turbine.
Blade.
Then what we do? We have some gearboxes, right?
Through gearbox, it will be transmitted to the shaft.
Now,
yes.
What your wind will try to rotate the turbine, but for a given wind speed, necessarily whatever the speed the turbine is rotating may not be the speed for that given wind speed for which it would have delivered maximum power. This, what I meant by this is that for wind, there is a characteristics just like the solar. Am I audible?
Yes, sir.
I think the network is frozen. All of you can hear me, right? So the wind turbine has some characteristics like this at different wind speeds, for which at a particular wind speed, if you rotate at a particular speed, if the turbine is rotating only for a given wind speed, for example W1 wind speed, this is wind speed, okay, and N1 is the NT1 is the turbine speed corresponding to maximum that given wind speed. So if you can rotate the turbine at that speed, then only the turbine can push the maximum power that it has kept from the wind. But naturally it will not do so, right? Because the wind speed is flowing and the turbine is rotating. That rotating speed of the turbine may not be equal to the maximum power point speed that it should have rotated to push the maximum power. So what you do, you have some arrangements into the generator to generate torque. Because generator will generate what kind of torque? The generator mechanical torque is positive for a generator and electrical torque is negative. Remember, for a generator, mechanical torque is positive because the prime mover is actually rotating the generator, and that is backwards. So electrical torque, if you can control using some arrangement of the generator to actually, if you can have control over the electrical torque, you have the net arrangement, wind turbine plus generator. That net arrangement you can move at a different speed by generating different torques, in electrical torques of the generator, because those systems are coupled, wind turbine blades plus generator arrangement, and by changing or controlling the generator torque, you can change the speed of the overall system irrespective of the wind speed. You regulate maximum power point speed, which is this one. But remember, this turbine speed and generator speed are different. Because this turbine speed is slow, that generator speed is fast. So to step it up in that range, a gearbox arrangement is used. So that is the whole essence. So what kind of MPPT is this? Electrical, mechanical, or both? Can anyone of you tell me? For winds, what kind of MPPT do you see? Electrical, mechanical, or both? I want to hear answers.
It seems mechanical.
It's both mechanical because of the turbine characteristics, and since you want to match it using the electrical characteristics of the generator, it is electrical, and
Yes,
it is
sir.
both also. So it's electromechanical MPPT that you do in wind. So both electrical and mechanical together we try to do MPPT. This is a different essence, complete different essence compared to that of the solar. But remember one thing, that the generator can sometimes, the generators are designed to push the power, but you need to do proper control, otherwise they can behave as motors. If there is no control, it may happen that the generator becomes motor, right? If surplus power is there, it can flow back to the generator and it can start, not see and just tell it is rotating as a generator, because seeing only with eye will not give you any feeling whether it is actually operating as a generator or it is taking the power from the supply and operating as a motor. Because for AC machines, either it operating as a generator or motor, it rotates as in the same direction. In DC, it is opposite. In DC machines, if it is operating as a generator, if it rotates anti-clockwise, for a DC machine, if it is operating at a motor, it will rotate in the opposite direction. But for AC machines, this is not true. For AC machine, the direction of rotation of generator or motor are both same. You cannot see. You need to analyze the power and the voltage and current phase difference to analyze whether it is pushing power or taking power. But in terms of generator, it should push the power. So proper control is necessary of the converters. So there are control techniques, and you can go ahead and study those control techniques. How we have back-to-back converters with the stator terminals to allow the regulation of the voltage and frequency, and also enable the MPPT operation by controlling the current. Controlling current means controlling the torque of the machine. You can actually change the speed. Some kind of field-oriented control you must have heard of, and you can make the total system operate in the desired speed range, such that the MPPT operation, due to the mechanical characteristics of the turbine, is enabled for that given wind speed. You want to trap the maximum speed from the turbine and then push it through the generator into the grid. That is the complete essence. But likewise, as solar, the wind conversion systems are also designed only to push the power, not take power. So wind conversion systems are designed to only supply power. That is the whole essence of the discussion. So hope you understand, right? Now read this question. These are very simple questions. 2 questions, 5 minutes each. Okay. After that, we can stop. So read the question. Read carefully, okay? Once you are done, tell me. So BDDC means bidirectional converter, right? I for first. Done, right? So this question is telling you a wind turbine which is generating 20 kilowatt of power, but 20 kilowatt is rated for rated wind speed. So rated wind speed is 10 meter per second. Now, as someone was telling, that this was a wind turbine and it is coupled to some generators, which is the synchronous generator. And then this generator is having AC terminals, which are connected to some converters. back-to-back converters. Having this link for voltage and frequency regulation. And again, this converter will transfer to AC and then plug it to the grid. So this is the arrangement. Now here you have also incorporated a battery, 500 volt battery, to smooth the power at the grid side such that it can take and supply power during emergency times, irrespective of fluctuations in the wind speed. We can smoothen the grid power. The battery action time or response time are very fast. These are not electrical systems. These are electromechanical inertia. You cannot tell that 0.1 second my wind speed was this and 0.2 second my wind speed is this. These are slow varying systems for which the power is also slow varying, and power is quite irregular in the wind, as you can understand, due to varying weather conditions. So to responsive to the load or fast, you need to incorporate battery energy storage, which provides a smooth power smoothing action to regulate the grid side fluctuations or to restrict the grid side fluctuations, even if the generation is having fluctuations due to varying winds. So where to incorporate? I have incorporated a battery here. So take out the positive terminal and incorporate a battery. But this battery is interfaced to the DC link using a bidirectional converter. It is like this. You have some inductor here and you have two switches. That is a leg. And to the DC side, you connect it. So this is VB, which is given as, obviously this side will be at a lower voltage due to the is at a higher voltage. This side, higher voltage side. Okay. So this is a wind turbine. This is the wind generator with gearbox arrangement. And after this, you have the machine side converter. You call it MSC. And you have the grid side converter, which you call GSC. Back-to-back converters required for speed regulation and power processing, right? So you have the battery also to store the wind power or to smoothen the grid side power. Using some proper need to utilize proper controlling. But these are the arrangements.
Sir, smoothen the grid power means that
Huh.
it is battery is supplying the losses. Smoothening
I will
means,
tell.
sir.
Smoothening means that, for example, wind speed abruptly drop. Okay, but you want your grid side power to be smoothened or to be constant. For example, you want your grid power at any cost to be 10, but your wind power previously was 8 and your battery was supplying 2. Your drop to 4, but I want 10 here. How much will I give from the battery now? Previously it was 8 plus 2. The wind was doing 8 and battery was doing 2. 8 plus 2, 10. Now I want this to be 10 only. So now the wind power due to drop in wind speed to 4. What should I supply from the battery to make it 10? Yes.
Yes, sir. It should be 4, sir. 4. 8, 6, 6.
And plus
Sir,
what?
6 plus 4,
So
it
6.
will be 10.
This means that power is smoothened, right?
Yes,
You not
sir.
see those fluctuations. That means power smoothening by battery. But how you are controlling the battery? Using a bidirectional DC-DC converter. So these converters are quite common and are mostly used with battery control to control the battery, right? Otherwise, directly interfacing the battery, don't have any control over the battery current. So if you have some converter which can regulate the battery current, you have control over the battery current, right? Control over the battery current. So to gain control over the battery, we need to interface it not directly, but using a DC-DC converter, which is termed as BDDC. Okay. Now read the remaining part.
Yes, sir.
Carefully. One second. One second from the starting. Carefully. I think it is done, right? So now you know the system, how the system looks like, and you know that you have two sources. One is the wind, another is the battery. Right.
Sir, wind is generating AC, so MSC is doing AC to DC. So to
Yes,
the
yes.
DC link.
Yes.
Yes, sir. Yes.
So now what I'm telling, you know that the wind was should have generated 20 kilowatts at 10 meter per second, but that wind speed is now 5 meters per second, and you know that your wind power is proportional to wind speed Q. So can you tell me that PW size of wind for 10 and power of wind for 5 is related as V10 cube by V wind 5 cube, right? So what is V wind, P wind 5? It is P wind at 10 into P wind at 5, V5, V10 at V wind at 10. So what is the answer? What is power of wind at 5? Wind power at 5 meters per second is wind power at 10 meters per second multiplied by velocity of wind at divided by velocity of wind at 10, which is nothing but 10. So 20 into 5 by 10. So what is it? 10. 10 kilowatts, right? Sorry, cube is there, right? So what is the answer?
1.25 K.
Two 2.5, right? 2.5 kilowatts. So wind is generating 2.5 kilowatts at 5 meters per second. But what is the question asked? That you have designed to provide smooth power at the grid of 10 kilowatt. You want your grid injection, that is the power injection, your grid with 10. But your wind power has decreased. Your wind is injected 2.5. You want here to push 10 kilowatt. So how much will you inject with the battery? Tell me. 7.5 kilowatts. Correct? 7.5 kilowatts you need to push with the battery. 500 volts. So what is the battery current? Power of battery, power delivered by battery divided by voltage. So what is it? 7500 divided by 500. So what is the battery current? 15 amps, right? This is the answer. Simple question, right? Any doubt?
No, sir.
Simple, right? I hope 15 is visible. Battery current.
Yes, sir.
And my screen is only lagging. So see the next question. Next question visible on screen?
No, sir.
Okay, let it go.
Visible, sir.
Okay, so time is I think complete. So you just see this. We'll take it up in the next class. This one and another problem I will cover, 2 problems, and then you can just do a revision, right? Tomorrow also. You take a screenshot of this problem and think about it. It is interesting, right?
Sir, sir.
Okay.
If you put the voltage as 500
Okay,
volts,
okay,
that is
sir.
battery voltage, sir.
Yes, I cannot hear you.
Sir, voltage you have put in 500, sir. 500 is related to battery voltage.
Correct. Not DC link voltage. It is battery voltage. So battery is interfaced with the bidirectional converter to DC link. But I calculated at the DC port the powers coming in and the powers going out, because that converter is handling that power. Who is handling that power? This DC link converter, GSC, okay, grid side converter. So I am doing power balance at the grid side converter. Whatever power is coming in, whatever power is going out should be equal, because the DC link voltage is constant, right? So I knew that the 10 kilowatt is pushed to the grid because the power smoothing control, right? So now the wind is 2.5. So remaining is pushed by the battery. Now I know the battery is pushing 2.5, sorry, 7.5, and the battery voltage is 500. So the power balance I do, because bidirectional converter, you don't have to consider losses. So you can do it, right? Accordingly, we can find out the battery current from the power. Right?
Okay, sir.
Okay. So we can tackle 2-3 problems of multiples, and then your microgrid, one interesting, very interesting problem. And
sir, in the final exam, sir, will there be some theoretical question also or only numerical, sir?
Anything can come in the final exam, but it will be conceptual, right?
Okay,
Both
sir.
sides can.
And,
Okay.
and sir, from assignments, there will be some questions, sir. From assignments.
Assignments, yes, obviously the things
Means, sir, concepts
the
will
course.
be.
Concepts, whatever we have discussed in the session, and whatever we have there in the assignments, and I have given you more or less all the concepts that are there, right?
Yes, sir.
So accordingly, the things you should be able to solve. No worries, okay? You just hear the sessions, hear the lecture slides, and see the lectures of professor, and then you solve the assignment questions, and you see the slides. These slides are also shared with you. You solve these practice problems, and then you can tackle and you see the session also. Whatever we are discussing in mouth interaction, that is also important, because whatever we are discussing,
Yes,
all
sir.
the things
Yes,
are
sir.
not right. So these concepts are very important. Not the solving only the problem will help, but the concepts, like you see the next problem we'll take up in the microgrids, the concepts are important. You will not find it written anywhere, right? So discussion is more important. So I hope next tomorrow we have a session. 5 to 7, normal session, your Sunday session. And that will be the final session. So I suggest all of you to come with some doubts, because you should have some doubts and we can discuss. And firstly, I will plan that for the first hour, I will try to cover these two problems and the multiples in the first hour. And then the next hour, we can tackle all the doubts and some revision. Okay. And we can always be available for we can ask the WhatsApp. So I think.
Okay, sir. Thank you, sir.
Okay. So tomorrow see you at 5, right? 5 to 7.
Okay,
Tomorrow
sir.
session. This is the last. You have the doubt and the problems. Try to solve problems.
Okay, sir. Good night, sir.
Okay, so you can leave. Okay.